Okay.
So for,
Okay.
for this
Please.
paper, actually there are two kinds of papers. They are quite similar. One is for this TreeCaps tree structured, and another is for TreeCaps tree-based capsule. And one is published on the NUS 19 workshop, and there are four others. And another is published on AAAI 21, and there is three others. And the two others are the same as this paper. And we first look at this paper, and these four others. The first is a researcher associated with A star, and the second is actually a PhD at SMU. So actually, this is the cooperative paper between A star and SMU. And for this
There
paper,
are small mistakes. I think Prof. David Lu get his PhD degrees in NUS.
Yes, yeah, I think I forgot to delete it. Okay. Sorry. So that's actually two kind of similar paper. But today I will first go to the Capsule network and then go to the first paper. Okay. So what is Capsule network? It is first put forward by the Clinton in 2017, and there are many. Every year he published one paper about the Capsule network, and today we will first introduce the first two papers and introduce the Capsule networks. So first we look at the CNN. Convolutional neural networks are awesome. They are one of the reasons deep learning is so popular today. They can do many, amazing things that people used to think computers would not be capable of doing. But they have their limits and they have fundamental drawbacks. So we first look how do CNN works. The main component of a CNN is a convolutional layer. Its job is to detect important features in the image pixels. Layers that are deeper, closer to the input will learn to detect simple features, such as the edges and the color gradients, whereas high layers will combine simple features into more complex features. And finally, the dense layers at the top of network will combine very high-level features and produce the final classification predictions. Here, I give you a very simple example. Imagine a face. What are the components? We have the face, the two eyes, a nose, and a mouth. For CNN, a mere presence of these object can be a very strong indicator to consider that this is the face. So here is a very quick question. Can CNN predict the right picture at face this picture right? Anyone volunteer? Can CNN predict this picture at face?
Probably, because it contains all the elements in face.
Yeah. So actually, the CNN not consider the whole structure, but consider the the local structure or local features. So it will also regard this picture also a face. So here is the question. So we will not talk about very detail about the CNN. I think everyone have familiar with this. So just a quick review. The artificial neurons output a single scalar, and for each kernel replicate that the same kernel weights across the entire input, and then output a two-dimensional matrix where each number is the output of that kernel's convolution with a portion of the input value. So we can look at this two-dimensional matrix as the output of maybe replicated feature director. Then all the kernels matrices are stacked on top of each other to produce the output of a convolutional network. And then we will do a max pooling, you know, we, you know, that consecutive looks at regions in the above described two-dimensional matrix and selects the largest number in each region. It is the max pooling. And as a result, we will get what we wanted, you know, an invariance of activities. And the invariance means that by changing the input a little, the output still stays the same. And the activity is just the output signal of a neuron. In other words, when the input image, we shift the object that we want to detect by a little bit, the network's activities will not change because of max pooling. Okay. But Hinton think the max pooling operation in the CN is a big mistake, and the fact that it works so well is a disaster. Just like what I have talked this example, because the max pooling, if you change a little, the max pooling will still give the same result. So an important thing to understand is that the high-level features combine low-level features as a weighted sum. The activation of, you know, a layer will multiplied by the following layer neuron weights and added before being passed to activation. So the features will, how to say it? So there is a, you know, the translations and the rotations relationship between simple features. So here, this example actually contains the translation and the rotation. The eye have a translation to different position. This means translation. And there's no rotation, but I think everyone knows what is rotation. So if that contains some translation and the rotations, CN maybe cannot figure out the relation. Actually cannot figure out the translation and the rotation. Okay, so
so here maybe I have small questions regarding your questions. So I would just want to rephrase it. I'm not sure whether I'm understanding correctly. So would you please go back to the previous slide and the previous one, the place one, yeah, the previous one. So if I understand it correctly, and also Xiangling mentioned that, and I do believe that for the right part, it's actually not a face, but it includes all the features of a face. In this regard, the CNN or the prediction layer will still extract some kind of features in the predicted face, right? So, but my concern is that when we apply the convolution layers, layer by layer, the features, the eye of the features, for example, this is supposed to be eye, right? Suppose we have millions or thousands of this face, and those face will always have eye in this position. Am I right? Hello. Can you hear me?
What does it?
Yeah, I got what you mean.
Yeah, my point is, suppose we have an image. These images have such a spatial relation. So if the model extracts features of eye, so after multiple layers, and we finally find a feature map, and almost these areas would contain the information of eye, right? Suppose the eye appears in these positions, isn't will cause the model make a different prediction? So that is my intuition there. Maybe Dr. Xiaoyan can make a comment because you work on an out of distribution problem. So if I make them simpler, I'm not sure whether my interpretation is correct. I just raised it here for discussion. So suppose a feature map, if we flatten a feature map, suppose the feature map is n times n. So suppose we flat n times n into n square vectors. And usually the feature of the eyes only appears in maybe several positions here, right?
I don't think so.
You don't
Because,
think so?
yeah, the eye's position is not fixed.
But eye will actually usually appear in this region, right? So this is a distribution of the training samples.
Is
So-
it possible, like, for a single feature map, it only wants to find whether this image has eye, just these elements, and it doesn't care about
But we
which.
apply convolution layer, right? So the
Yes,
convolution
so
layers will.
for
Mm,
probably
is-
for this single feature map, it only care about whether if there's an eye exist, right?
Really? Is that feature so
Like
powerful?
for example, I'm not sure, but for example, you may have different several feature maps, and one is looking for eye, and the other one is looking for mouth, and then finally you combine all
My
those.
gut feeling is not
Mm.
possible. I'm not sure I'm 100% correct. My gut feeling is
Mm.
not possible because the neural network model highly depends on the position of each feature. So a very straightforward is that if the eye always appears here, the next time the eye appear here, the model will not. Suppose, for example, let me say that suppose this is a picture.
But
Suppose there's
when
a
you
cat.
do-
Suppose there's a cat here, right?
Mm,
And if the cat always appear here, if one time the cat appears maybe here, in this case, the model may have a problem. If we want to address this problem, we need a lot of data augmentation
yeah.
to make the model to do the trick.
Mm.
So my point is that if the eye always appear in this position, and after many epochs of training, the model will just locate on the features in specific feature map to do this. So another gut feeling is that images look like these may not be well handled or predicted as a face. So that is my gut feelings. But anyway, you can make a point that the CNN only look into the local features. And there's no connection between the global relations about those local features. I buy the point. But my small question or intuition is that because CNN usually still cares a lot about the spatial positions. If the eyes always appear there, just looking at this example, I feel that if a neural network model trained from thousands of the normal face, it may have the problems to recognize this kind of the out of distribution samples, right? So that is just my gut feeling.
Yeah, I think your question is about the coordinate. So you have a x, y in the picture, and you thought maybe the eye will be always a fixed x, y, a fixed coordinate.
Yeah, a fixed region. So if the eye always appear in a fixed region, and if the eye appears in the
about this later. Hinton also talk about the coordinate or the position in the picture, but he thinks the CN can't capture this information.
And another follow-up question, maybe I raised these questions too early, is that if we want to address the global problems, we can just use self-attention, right? So to address, once I don't know if you still remember the guy named Yang Hwee. So he was trained self-attention again. So once he using some normal approach, the normal deconvolution layer to train again, and we'll find the eyes, nose, mouth actually are in very weird positions. That should CNN only capture local features. But if we apply the self-attention layer to capture the relation between the global relation there, then the face will look quite normal. So another of my questions, I understand when you raise this point, when you say that CNN does not capture the local features, we want something capture the global features. So maybe I raised this question too early. My question is that, comparing to the self-attention, which can also capture the global relations, and what is the advantage of the TreeCaps? So maybe I just prepared the question here, then no need to address it now at this moment, but maybe I will raise the questions later.
Yeah, and
maybe Dr. Lin, did you remember I drew some attention map previously for each layer? Did you remember? Use GradCam. So I remember that actually in some layers they indeed focus on some local information. For example, if the MINIST data set, sometimes in different layers they have different local focus.
Yeah, I understand.
So, yeah.
I understand. So the point is, you can see the CNNs were passing the feature map layer by layer, right?
Yeah.
So suppose they look into these areas. The next time when we becomes a feature map, the next feature map may look into these areas, and the next layers may look into these areas. But anyway, those features only focus on this local region.
Yeah.
Right. So I fully agree with you that a CNN will have to focus on the local regions. By the way, what's the point of your attention layers, the GradCam, to using the GradCam to find the attribution problems?
Yes, contribution. So my point is, I agree that indeed this is a problem, but I still cannot image that why it can predict the right one as a face. I still think about this.
Yeah. So I don't know, because it looks to me like the out of distribution error. If you can input repair, you can reorganize the face into a corrected face. That will be another perfect input repair solution, right? Because it's really a fixable out of distribution problem.
Yeah.
Okay, so I think there have enough discussion here. Anyone have a question? Okay,
maybe
please.
can I ask another one?
Mm.
So for most machine learning models, invariant to translation or rotation is a good property because it's more robust to perturbation. But for capsule, it is not it's not that robust. Does it mean capsule is more likely to be attacked by small perturbation?
yeah, I think so, because they actually didn't consider the translation and the rotation.
Oh, okay.
Rafa, your point is that most CNN requires rotation, and
Most machine learning models.
yeah, so they also need the rotations and
But I think most machine learning will the convolution neural net will be affected by rotation and translation. If you have some rotation or some translation, they will output a different label. They will.
Yeah, definitely. So that's why you can think about it. So if we, for the network, for the neural net, for the most CNN, they require data augmentations to detect those kind of the transformation. It means that without such a transformation-based data augmentation, and the model may hardly recognize it is a face or the identity of the people, right? So that's my question. So even the transformation like rotation, the model will have a problem with that. Let alone such a radical change. The mouth is up, the eyes will be scattered everywhere. So I just feel it weird, but I fully agree with Yufan on that. CNN only capture the local features. But for this example, I just raised a question for discussion. Yeah.
Okay, so and here is actually the capsule network, and it also used a part of the convolution, but he adds a capsule structure behind the convolution network. So that's a quick architecture, and then we will go. We have discussed about the drawback of CNN, and I'm actually Hinton raises list 5 points of the drawback of CNN, and in the in a triple AI 20 conference. So maybe anyone can give some example. Here I share example to check whether the CN actually didn't have, because people can have some feeling of the coordinate, or you can say the direction in the picture, but the CN can't. So anyone can share more about the weakness of convolution network.
So this is
For example, this is the open question. For example, here, if you look at this picture, which country you may think about it, or which, if I said it is a part of a map, the Earth, a part of the Earth map. So which country you think it is? And
Singapore.
Australia.
so yeah, some people may think it is like Australia,
Australia.
also is like Singapore. But if I said it's actually rotate the picture, like if you rotate the picture like this direction, then which part of the land you think about it?
China.
Brazil.
Yeah, so you will get different answer, and my answer would be the Africa. You may think this is a bit like the Africa.
Okay, you mean you don't mention how much degree you rotated, right? So you rotated 90 degrees is Africa.
Yeah, and
Africa is a continent instead of country.
yeah. So for the right picture here, do you think this is a square? Or you think it's a diamond, or you could say rhombus?
So yes, I understand. So looking from different angle will give us different answer. So what's the point of the CNN? Why CNN is bad on there? On that?
Yeah, because the CN can't explain this situation. Can you understand this? The design of the CN didn't include this sense of human. Or you can say the CN actually have different recognition way or recognition pattern with human.
But I think if we criticize CNN in this sense, we expect too much of CNN.
Actually, Hinton just want to he lists the 5 points, and he want to figure all of them, just solve all of them the problem using the capsule network. So anyone can have some more ideas about the weakness of CN. For example, in the adversarial attack, if you add a random noise on a picture, the CN will output quite different labels. Maybe I can just show you here. Hinton lists this example. The original picture you can see is a car and is a dog. But actually, if you add a random noise from human eyes, you can't see any difference, but the model will output very different labels. So in that case, Hinton thought, the CN do not recognize objects the same way as humans. Any question here? And for the right problems, he thinks that the CNN actually do not understand images in terms of objects and their paths. So so the main point is that the CN don't understand the picture as human does.
Okay.
Okay, and for the past example, he talked about the viewpoint. So I think this is a very important point. I give you some example here. So I didn't go to the New York, and I only look I only read some articles about the this how to say this picture, but actually you can find that these 5 pictures all regard to the same thing. It's for human, but the machine will not, the CN will not work as good as humans. So this is because they thought, because Hinton thought is because it is 3 dimensions, but the picture only have 2 dimensions. But however, the human can understand 3 dimension objects. Can you understand this?
I find this is a common sense. Yeah, I can keep going on.
Yes, so the Statue of Liberty, I don't go to this, but I can figure out that these are the same thing, but maybe the CN can't figure out these 5 pictures are all the Statue of Liberty. So the Hinton thought that we human not depend on 1 view angle, but on a 3-dimension angle. So it he copied some idea from the graphics. From visual information received by eyes, they construct a hierarchical representation of the world around us, and they try to match it with already learned patterns and the relationships stored in the brain. So this is how recognition happens. And the key idea is that the representation of objects in the brain does not depend on view angle. So at this point, the question is, how do we model this hierarchical relation inside a neural network? The Hinton copies idea comes from the computer graphics. So in 3D graphics, the relations between 3-dimensional objects can be represented by a so-called pose, which is in sense the translation and the rotation. So for a CN, this task is really hard because it does not have this built-in understanding of 3D space. But for a capsule network, it is much easier because these relations are explicitly modeled. And the paper about the capsule network used this approach, was able to cut error rate by almost 50% as compared to the previous stage of that. So this is a huge improvement. And another benefit of the capsule approach is that it is capable of learning to achieve state-of-the-art performance by only using a fraction of the data, a small data set. Because like our humans, although we don't go to the New York, we don't see the Statue of Liberty, we can recognize the Statue of Liberty only through a few pictures. So a CN would use a large data set, but however, the capsule network only use a small data set. So in this sense, the capsule theory is much closer to what the human brain does in practice. In order to learn to tell digits apart, the human brain needs to see only a couple of dozen of examples. And the CN, on the other hand, needs tens of thousands of examples to achieve very good performance. So, which seems like a brute force approach that is clearly, different from what we do with our brains. So actually, the Hinton wants the network to be like our human brains. Any question for this part?
It sounds more like a philosophical point of view about fusion learning. Maybe you can keep going on to have bring us to more details.
Okay, so here is the key point: is the hierarchical relation inside the representation of a neural network. And here is the example used by Hinton. And you can see in the computer graphics, he used rendering. This is rendering. And he get a rectangular and a triangle in the picture, and it with his the position and the the translation and the rotation, and then it will get an image. But if you have different translation and the rotation, it will have different picture. So this is a boat, this is a house. So this example is want to show that the translation and the the rotation will, how to say, will make a difference.
In that within the position with different positions of rectangle and triangle, it will cause different semantics. In this slide tell us this.
Yes.
Right. So in this case, how
We need to
yeah.
model this information.
Okay, you can keep going on. I keep my question. Let's see the next few slides.
Okay. So this is the Capsule do. The Capsule will I think they want the Capsule will have this this architecture, or this attributes. The length will estimate the probability of the presence, and the orientation will stand for the object's estimate pose parameters. So they want to learn these two Capsule networks. This Capsule network will represent this, and this Capsule network will represent this. Neurons. This Capsule neurons will represent this direction and this length, and another will represent this length and this orientation. So they want to do this. Okay. So how they do? The most thing is that they want to represent not a scalar, but to be a vector. So they want to this vector to contain both the translation and the rotation information.
Do you mean for any object in the image that wanted to like look at it from 3D point of view instead of 2D? Is that what you?
Yeah. So the first thing is to recognize some local features, or you can say some triangle or some square, and then you want to also recognize the the angle, the length, or the orientation, and store them as a vector. So this is different from the Siang. Here is the comparison. Capsules encode probability of detection of a feature as the length of their output vector, and the state of the detected feature is encoded as the direction in which the vector points to, some parameters. So when detected features move around the images, or its state somehow changes, the probability still stays the same because the length still the same, but the orientation changes. For example, so image that a capsule detects a face in the image, the path face, and then output a 3D vector of the length of 0.99. Then we start moving the face across the image. The vector will rotate in its space, representing the changed state of the detected face, but its length will remain fixed because the capsule is still sure that it has detected a face. This is what Hinton refers to as activity equivalence.
So we still need to detect the objects in the image, right?
Yes.
Assuming that we detect an object, we apply a vector on these images. If I understand it correctly, we apply translation and the rotations along the way to it sounds to me it's more like a special kind of the data augmentation.
Yeah, maybe I can go to the details of the capsule neurons. Then we may got some ideas.
Yeah, so there's the affine transformations.
I will
within-
talk about each part, the 4 parts of the capsule neurons, and then maybe we can get a more understanding. Okay, so we go to the 4 parts. The first part is the matrix multiplication of input vectors. So here is a face. You can see in this image. For example, you just image that this is depends on the nose, and this is the feature of nose. This is a feature of eyes, and this is a feature of mouth. Okay. So the length of this vector encodes the probabilities, whether it is the nose or this, whether it is a face, whether it's the eyes, whether it is a mouth. Okay, the length is the probability, and the direction. The direction of the vector encodes some internal state of the detect objects. So these vectors then are multiplied by corresponding weight matrix W. This is a weight matrix W that encodes important spatial and other relations between the lower level features and the high level features. So this, let me use a different color. So this is 2 different capsule neurons. This is a low level, like the nose. This is a high level, maybe the face. So this matrix actually have for example, this matrix may encode the relation between nose and the face. And the face is centered around the nose. So the size may be like 10 times of the size of the node. And its orientation space corresponding to the orientation of the nose, because they are in the same plane. And a similar intuition can be drawn for the other matrix W. So after multiplied by this matrix, we can get what we can get is the predicted position of the higher level features. In other words, these 3 vectors may represent where the face should be according to the detected position of the eyes. So these 3 vectors maybe depends on the faces. So can you get this? So you depend on the nose, depends on this nose, you will get a face. And it depends on this eyes, you will also get another face. So if these face location closely match, that there must be a face there. So this is the intuition behind the capsule network. Any question?
I think I roughly got a point, but I still need to digest a little bit. Anyone would like to raise a question to maybe clarify the concepts?
So the low level is actually the.
I got a point. I got a
Yeah.
point. So the point is that you first detect the low level features like eye, eyebrow, nose, mouth, etc. And based on each individual, you try to predict it. Suppose we know this is a nose, and where the face supposed to be, where supposed to be the face, right? So based on these features, you want to find an overlapping face there.
Yeah, I think this is the intuition behind this calculation.
But in this case, why? I don't know how to raise the question, so I'm still trying hard to compare it with the self-attention. So the self-attention just to capture the relation between given a nose, we're supposed to be the mouth. Given eye, we're supposed to be the eyebrow. So isn't that they share something similar?
Yeah, actually, I think the self-attention, the similar is because is about the similarity. That means the self-attention actually is the similarity between the local features. Okay, and here is actually the similarity between one small thing to a large thing. You know, the part and the whole. Here is the similarity between the part and the whole, and the self-attention actually is the similarity among the whole, among the parts.
Okay, maybe we can keep going on. And but anyone would feel free to raise questions if you.
This is the part, the whole.
I got it. I got a point. So the example is that the nose and mouth and nose and face, right?
Yeah.
Anyone would like to raise question here? Feel free to raise questions.
Yeah, this part and the whole relation actually presented by the Hinton in Triple AI 20. He also spent a lot of time to say this philosophy, philosophy intuition behind this. Okay, so how to compute the similarity between the capsules? It uses the dynamical routing. So here is the algorithm. Let's look at the algorithm. First we go to the intuition. So the lower level capsules will send its input to the higher level capsules that agree with this input. Okay, so the most important is like the agree. Agree actually, from my part, actually the similarity. So you can see that the similarity actually the same. They use the dot product, the same as the self-attention. The self-attention also use the dot product to stand for the similarity. Okay, we go to the detail of the algorithm. The first line. The first line says this procedure takes all capsules in a low level L, and their output is the U, as well as the number of the routing iteration R. Okay, so this is the iteration R. Maybe it's a fixed number. It's a fixed number like 1, 2, 3. And the very last line tells you that it will produce the output of a high level capsule V. Okay, so it's just from low level capsule to a high level capsule. And then we go to the second line. The second line, you will notice that there is a new coefficient, the B. The Bij actually is simply a temporary value that will be iteratively updated. And after the procedure is over, its value will be stored in the C. In the C. So just regard this as a temporary value. And the line 3 says that it will do some iterations. And the step 4 calculate the value of C. Calculate the value of C, use the softmax. So this C actually is the weight. Okay, so let's go to the line 5.
By the way, can you be more specific on the BI? What is BI for?
The BI is actually a temporary value that depends
from the very beginning. So the vector BI is all the same, right? It's all is a uniform distribution.
Yeah, 0.5. The CI will be 0.5 because all the BI is 0.
0.5. Really? I think it's after we apply softmax, it's supposed to be a uniform distribution. Suppose there n dimension, the CI is supposed to 1 over n. Right? Because all the BI is 0. So you apply softmax, error 1. Right?
Yeah.
I think because
It's 1/n, right?
yeah, 1/n. If you have multiple, it's 1/n. So that's, I think this just means that all the capsule have the same weight here.
Okay.
So have the same weight. So if you regard all the lower level capsule as the same, so you will get use the 0 because this is the first initial state. And for the 5 step, you just weighted average all the low level capsule, and then use a squash. Squash is the activation layer, activation SJ, or you can say the normalize. And then finally you update the Bij using the similarity score.
I may miss something in the previous slide, but can you explain again what's UJI?
UJI is the low level capsule.
How do you define the value of UJI?
It depends on, because the previous is the CN. Yeah, then the CN decided the first layer of the capsule neuron, and then it will go to the capsule neuron networks. Then there will be multiple layers, and the first maybe the low layer capsule. The second, yeah.
And so what
I
does
think
UJI stand for?
UJI is the W matrix times U, right? So previously you are computing this.
Is it a trainable weight or you predefine the value of UJI?
The W inside U hat is trainable. So U hat is also not
Trainable.
fixed. Yeah, trainable.
Not fixed.
So it sounds to me like between the capsule layers is more like a fully connected network.
I think it's a bit like the self-attention.
Self-attention is still a fully connected network, right?
Yeah. So, but it's
But the point is that you learn attention.
Yes, the similarity is between the low level to high level. The self-attention is among the low level. Yeah.
Then it's just more like attention on different level, right?
Yeah, from my viewpoint.
So my question is that can you be a little bit more specific? Maybe I still missed something actually. So can you a little bit specify on the difference between SJ and VJ?
SJ and VJ.
VJ is actually an activate function, right? The squash is the activation function.
Yeah.
Okay, so you learn for each SI, you calculate the CIJ. CIJ is actually the B.
The squash is in the later.
Hey, Yufan, will you please mention again about UIJ?
UIJ hat is equal to WIJ times.
Can you write it? Can you write it on the screen?
It's in the previous slide.
In the previous. Okay,
it's when you know the nodes and then you.
And Yufan, please go to the previous slide.
And then you times the relation metric between nodes and face, so you get U hat.
Yeah.
So the WIJ times the U hat. And U hat is the weight or something else?
It's a capsule.
U is a capsule. So the capsule is the IJ.
This is the squash. So the first is the low level vector. And then after a calculation, you will get a high level vector.
Does the paper explain why they use squash as activation?
Actually, they think this is an innovation because this activation will let the vector has, the normalized less than 1 and remain the same direction. This is a scalar that will let the vector less than 1 or a bit small.
Okay.
It's more like the weights, right? Sj is more like the Sj mode is more like the weights. So the larger the weights, the larger the Sj, the more likely they carry more weights here. Am I right?
No, Sj is not a weight. Cij is a weight.
No, Sj mode is a weight. I think in the nonlinear activation function.
SJ mode.
Yeah, Sj mode. Sj
SJ
mode.
norm. SJ norm.
Oh yeah, Sj no, yeah.
Norm.
It's basically a weight.
SJ norm is a scalar value.
Yeah, I say that's just it's more like a weight. Am I right?
Wait, what's wait? Wait,
Well, and who is asking?
It's a normalization factor.
Oh.
you mean.
Yeah.
Hmm.
Okay, let's keep going on.
So weight is actually, I don't think this is a weight. It's more like a factor. So to make the vector a bit small. Okay, let's go. So it also have some example about the dot product. So I think it's quite simple. I actually prepare this for a quiz. So which one will get the largest number after the dot product? And then which one will get the smallest number?
You can find a volunteer to answer this one.
And which one will be the 0? New question.
Maybe you can find a junior student to answer.
Okay, maybe Junbo, are you here?
Junbo is not here, I think.
Okay, maybe Siang Hwee, are you here?
Hello, yes, I'm here.
So here is the product of two vector, and which vector or which result will be the largest?
I think A will be the largest.
Yeah. So which is the smallest?
Smallest, I think E will be the smallest.
Yeah. So this is actually, shows if they are the same, they are quite similar, they will get the largest number. So it's why the dot product can model the similarity. And you can check another for the right picture. So if the the lower capsule have the different direction of the high level capsule, it will make the weight goes down. And if the have the similar or the same orientation, they will let the weight become bigger. So this weight will this low level capsule will weight a lot. So this is more important. Okay, no question for the dot product. Okay, so how many iterations? The paper examined a range of values in the minutes and the cipher, and the result is that the 3. So more iteration tend to overfit, so 3 is better. Okay. So this is the slides copied from the video, the presentation by the paper, the Hinton, and you can see that we can regard the J and the K is a high level capsule, and here is some low level capsule. Now we want to project the low level capsule vectors to the high level capsule, and if they have the same, if they very close, they will get send more send more information. If they are not very close, it will send less information. So this is the intuition behind the calculation. Any question for this picture?
I have no questions on these, but my question is that how the number of the low-level capsules and the high-level capsules actually matters a lot for a specific task, right?
Pardon, please.
My question is that I have no doubt on the capsule calculations and the routing part, but it seems to me that the number of low-level and the high-level capsules are fixed, kind of the hyperparameters.
Fix the hyperparameter.
I mean the number of the low
Yeah.
level and the high level.
I think they are all fixed.
Yeah. So
capital is fixed.
yeah. So just like the CN and the RN, etc. So whether the number of the capsules matters. So suppose just for the trace, maybe 10 high-level capsules is already enough. But what if we have 20 or even 100 high-level capsules? And will that influence the performance of the neural network model?
I think it will.
And
Yeah,
how then the number of the capsules actually should be tried for a few times and defined
Yeah.
based on some domain knowledge.
yeah, you need to set the hyperparameter. So you need to check the model performance one by but there's some tools to quickly check, let the machine to decide which one is best.
Just more like architectural evolution.
Yeah. Here is the fixed. You can see this is a fixed. See, this is the fixed layers. Okay, so it goes back to the third step is the sum of the input vector. There's similar. And the fourth is the squash we have talked before. So this is additional squashing, and the blue one is the unit scaling is the same. Okay, so the squashing is to have the length of no more than 1, but does not change the direction. Okay, and then this is the visualize of the 1D squash. Okay, so let us have a quick conclusion of the causal network. So here is actually one neuron, and the U with no height. Since this is for the low level, and this was for the high level, and we'll use the capsule network, capsule neuron to calculate the final result. Any question for this picture?
It still seems to me like the tension, right? You add a lot of attention between the layers.
Yes, I think it's quite the yeah, because
so still another paper to justify attention is all you need. I don't know whether my interpretation is correct.
attention, yeah.
Have you ever read a paper? Attention is all you need. That's a paper introduced a transformer.
Yeah, and Hinton also used transformer as a decoder. He thinks the attention is good. Transformer is good. So in the latest version, it changed the 4 layers, the fully connect to the transformer. Okay, and here is the old version. Old version, the whole actor have 2 parts. The first is the encoder, the second is the decoder. The encoder is have 3 layers. The first is convolutional layers. It outputs the U. The U. It is the low level features that maybe extracts the nose, the eyes, the mouth, and then it fits to the 2 layers of the capsule. And the capsule, the 3-layer capsule, the 3rd layer is about the actual task. This is a mini test, so use a digital caps. So there's only 10 digital. This is the only 10 capsule neurons. And the intermediate layer is, I think, the most important part. Okay, so between the capsule, there is the dynamic routing. I just mentioned the algorithm. Okay, here is.
Yufan, do you have a question here? So in this kind of so I don't know whether I grasp the point. Why my gut feeling is there's a confusion between the fully connected, the fitting layers and those capsule layers. Let me make the maybe I missed something here. So after we got the convolution layer, so suppose we have convolution layer, we have a feature map, okay? And now based on what I introduced, this feature map will be fitting to the capsule layer, right?
Yeah.
The capsule layers. And in the capsule layers, they're trying to, and each feature in the feature map will be a UI, right? And then it will output some UJ based on the capsule layers. And basically the UI and UJ are intermediate neural network layer. Am I right?
Yeah.
And what's the difference is after what do we have the feature map and we connected with a set of the fully connected layer?
Because we need to use the routing.
The routing, you mean the
The
routing?
dynamic routing, yes.
Okay. The dynamic routing and the structure still looks a little bit similar to me. Between the routing and the fully connected layers. Would you please distinguish or clarify a bit between the distinct features of the routing compared to the fully connected layers? Because it seems to me that for fully connected layers, there is still a lot of the so-called attention structure there. But now the routing will have a few iterations for them to spread the weights. But what's the fundamental difference? Would we clarify a bit more on that part?
I think all the neural networks, contain some fully connect.
Yeah, I got that. But what to see? So the basic idea you can see you apply the effing transformation here, right? So let me continue. First, you apply the effing transformations and you add some the weights here. The weights need to propagate a little bit, and then you apply the squish here. It seems to me that there's nothing.
But the C depends on the similarity, so you can say that it's a bit like self-attention. But I have said actually this is a similarity between the high level and the low level. It's different. The self-attention is is among the low levels.
I mean the attention, just mean the attention. So let me think about it.
And
I get a point. So there's one layer, their concept attention. Suppose they will evaluate the similarity between the low level features and the high level features, and using that scalar or factor to design a network. And also there's a special final activation function called a squash, right?
Yes. Oh, I also use a picture. Wait for a moment.
And also how is going to capture
here. So here is the picture of attention. You can see that the attention actually calculates the between different nodes, between different
layer. You mean different layers?
Layers. You can say that. So it's different. The original attention is used to calculate the similarity between encoder and decoder. So for example, so this is a neuron in the encoder. Then I want to check how much similarity between one neuron of the encoder and the decoder. That means how much information I needed to get from the encoder. Okay.
So let me rephrase my question. So given the capsule layers, apart, I think the affine transformation is more serve the goal of fitting, right? Can you go back? Yeah, that's nice. That picture is about previous one. Yeah, this one. So this affine transformation is nothing more than a fitting purpose. And here, if I understand it correctly, it's just introduce several iteration to calculate here. It just add several iteration to calculate the attention between the low and high capsule.
I don't think this is called attention. It's, maybe you can call it similarity or something. But I think attention is more specific term.
But basically, when you calculate how similar these low-level capsules is similar to those high-level capsules.
Yeah. Yeah, I think it's like a inner optimization process. To make the weighted sum of U hat to be close to UJ.
Okay, let's keep going. Yeah, I think I cannot raise more questions given the time limit. Yufan, please go on.
Okay. And so quick review. The first three layers is the encoder, and the last three layers is decoder. So the encoder will get a loss function, and it predicts the number. It predicts the picture, the minutes digit. Okay. So actually, the loss function is quite easy. So if it is correct digit, so you only consider the first part, this part. And if it is greater than 0.9, this m plus is 0.9. So it is greater than 0.9, it will just zero loss. But if it's not greater than the 0.9, there will be some loss. Use the L2 norm. And if it's not the incorrect digit, can you understand this? For example, this is like if you predict 1, okay? So now the picture is actually 1. So for the 1 digit cap, the digit capsule, the TC is 1. Okay, the TC is 1, and the lambda, the 1 minus TC is 0. So don't consider this. So if for the second digit capsule, then it is a wrong digit capsule. So it will, here is the 0 and this is the 1. So it only considers the second term. And the lambda is for the constant numerical stability. And so we will only consider the here. And if the probability is less than 0.1, that means the model think this number is less probable, so it will get to 0 loss. If it's the higher probability, it will go to a high loss. Okay, so this is the loss function. It's not very simple. And after you predict the digit, and then you have the decoder. Decoder is used to reconstruction the picture. This is the predictor. This is the original picture, and this is the predict picture. So this layer, this decoder is used to update the parameter and get the reconstruction loss. Okay. Any question for the architecture?
Can I know for the loss, how do you get TC?
TC. So another explanation. Now there's many digit capsules. Okay, there's 10 digital capsules. Remember in this picture. That's
Yeah.
10. Yeah. So here, if the the golden label is 1, so the first digit
How do you
capital
know the golden label?
because I think it is in training. Let me check loss term for 1 digital. Yeah, I think it's for training.
Yeah, I know it's for training. Then how do you get this?
So the model use the golden label, then it will use the different loss.
The label is actually whether there exists an object there, right?
This is minutes, so predicts the number.
It's the classification label.
Yeah,
Okay. Okay. Yeah.
yeah.
Mm.
So if the original picture is 1, so you need to predict 1. So the first digital capital, it is stand for 1, so it will have the 1 TC. The TC will be 1 because it's the correct digital capital.
Okay.
Yeah, so if it is not the correct, it will be 0, and then you will only consider the second term.
Yeah.
Yeah, so this is the loss.
By the way, so a small question about the VC. Does there a range for the VC? Is there a range for VC?
Less than 0 or less than 1, right?
Normalized.
Yeah.
Oh, yeah,
Yeah.
because it's normalized based on the splash activation function, right?
Yeah.
Yeah.
Okay.
Okay. So in the AI 2020, Hinton, Li Kun, and Yang Shu, we can also present a 30 minutes presentation, and Hinton also get a new version of Capsule, but we didn't have enough time to show this Capsule networks, and he thought the past Capsule networks are all wrong, and this is the true one, the right one. Okay, so if you're interested, you can go to this link and read this presentation. And the most important part, I think, is that the previous version used the discriminative learning, and it represents the part-whole relationships. But now, Hinton thinks that we need to use the unsupervised learning that use the whole part relationships. And he used example said, if you know one star, because that's many star will goes to a whole picture. How to say that? Let me.
So what's the difference between the part whole and whole part?
Yeah. So one star. Yeah. So let me explain this small example. Here is the star, and maybe there are many stars, and then it will go constellation, a whole picture, So if you only know one star, you can't go to the whole picture. But if you know the whole picture, you will go to one star. So this is the difference. If you
how this information can get us to learn the design the model.
So Hinton thinks that we need to get the whole information, then goes to the part information. So it's different. Yeah. So how to get this?
So to design the CNN.
So he needed to redesign the capsule to let them present the whole information, then goes to the part information. I didn't contain this lecture here, so you may refer to the original presentation and original paper here.
The point is that if we go through the whole part relations, it will result as very detailed feature vector, or give us very large and detailed representation layer, right? So what we want to do is to learn a representation of an image or an embedding of this feature or feature. And we go from whole into the part, and whether will the representation vector be very complicated and very detailed.
I don't quite understand because it is very difficult.
Okay. Maybe we can just put this aside and keep going on.
Yeah, so I think if you're interested, you can go to this video. He explains very detailed, but I didn't quite get it. Okay, and then so maybe we can have a compare between the CN and the transformer and the capsule and the GN. So the CN actually gets the local information, but the transformer gets the information between some neurons, and the GN actually gets the information between the samples. So the capsule is want to, get some additional information. I have said that is the high level and the low level. This is the hierarchical information. So the comparison is that this is a local. This is between the neuron, and this is between the sample. The GN is between the sample, and the capsule is between the hierarchical, is the low level and the high level information. Okay. I think it's a bit about the intuition behind this model, this popular model. Any discussion here? Then we will go to the paper.
A minor question here. So if the capsule is basically a concept and idea, so maybe we can do something. Do you remember that I raised a question for self-attention, right? Self-attention is just to build the tension between the components to capture the relation or global relation of low components. But in this case, we can still introduce the idea of capsule. So suppose we have low level features, and then we're using CNN to capture high level features, because after we apply convolution layers, then the low level features will turn into high level features somehow in certain sense, right? Suppose we do that, we can introduce another layers to make a connection between low level features and high level features in the CNN feature maps. In this case, we can still capture something similar. Am I right? Or what do you think about it? Have I made that clear? So suppose given a layer, suppose we have a low level feature map, F feature map low, and after we apply one convolution layers, we have feature map high. Okay, so this is what we have for a feature map. But my point is that we add another layers about maybe capsule, something like this. We're trying to build the low level and high levels, further build a low level and high level between those feature maps. And then we can do something similar. So that's the idea that we're going to suppose this is maybe the n times n, and this is half n times half n, right? So this feature, so this is a high level and this is a low level. Basically, we can also introduce something like capture to build the relation between the low level feature map and the high level feature map. And then we finally get there. So we still capture the part and the whole relation. What do you think about?
But the CN, because quite easy, so you only use the max pooling I explained in the beginning of this lecture. So
yeah, I understand there's we can use max pooling here, but we can add an additional routing apart from this way, and we can add additional routing here to update the feature map here. You get my point?
Yes. So I think the Capsule actually just substitute the max pooling. They don't use the max pooling to get a higher level feature map.
Okay, okay. I think I still need to digest a little bit on this part. By the way, what do you think? Or maybe you have another picture. Let's quickly go, because given the time limitation, let's quickly go through another paper so we can have more detailed discussions in usability.
Okay, so go to the TreeCaps. So the TreeCaps is actually quite easy, and the task is program comprehension. Is just the representation learning. So just make the program to a high dimensional space, or frankly speaking, is just a vector. So it's used for the downstream task. It's classifying the function of many programs. Here, in this paper, it just classify the sort algorithm. So which sort algorithm this program belongs to, like the bubble sort, like this. Okay. So the intuition is that the first is that the program language have very defined grammar, rigid syntactic structure, and they can be unambiguously passed into syntax tree. And the second intuition is that there contains complex control flows and data flows. And the third intuition is that there are some color informations, and they just want to use the AS tree. So the AS tree, they first use the word to vector to let the AS tree become vector. And then he thinks that if we want to use the capital network, the major difficulty is there's two major difficulties. The first is that the tree structure data are inherently different from the image. And the second is that the tree size varies from program to program. So there are no fixed size. So they want to use some techniques to change the data, and then they can use the capital. So the capital network is just the same, but they do some tricky to change the data. The first tricky is the binary tree kernel. It is published by the Mo 2016, and just use the binary tree kernel. So now this is the kernel is become a binary tree here. So the original, like the square, is a 3 multiplied with 3 square. Now it is a binary tree, and for each node there will be a different weight, like different W. So they just use the curve.
I know there's little time for me to raise more questions, but my question is that how do they translate a non-binary tree, sorry, in binary tree? So the tree is a representation of the code, right?
Yes, there is a AS tree. Okay, so they want to do convolution. So, but there's no square convolution. There are no 3 multiplied 3. So they just do like here. This is a convolution. Understand? This is another convolution. Understand?
Yeah. So no, this is another question. My question is that an AST is not necessarily a binary tree. And how do you translate AST into a binary tree?
No, they just consider it is a binary tree.
It may miss a lot of information.
For example,
there's a AST node called a method declaration. And for method declaration, you have a lot of children, like method body, the parameters, and the parameters have a lot of stuff. So, and also there's comments, signatures, etc. So it is not necessarily a binary tree.
No, not just not delete this, but consider this as a binary tree. Like for example.
Yeah, it's a binary tree. We must converge the nodes, right? And how do they merge the nodes?
No. Don't convert. Like here, there's 3 children. Okay, so they do this, and
okay.
Yeah. So another one is for A, B, and the root. Okay. So they just consider this as a binary tree. Understand?
What if there's only one child?
Only one tree, there's an empty node.
Okay.
Yeah. Any question?
Okay, keep going.
Okay, so and another trick is that because the number of capsules is variable, because once code have different, the code is different, so the picture or you can say the AS tree is different. So we can't use the dynamical routing. So because the dynamical routing have fixed number of capsules I have mentioned, so he used the statical routing. So statical routing is just what? So he just sort all the capsules and get the
First,
number of capsules. Fixed number. He used the top A code, or you can say top A node in the S tree, because he thinks that we know the length of the vector shows the probability. So he just normalized to L2 norm.
Okay.
Yeah, so quite easy tricky. So after these two tricky, you can just copy to the TreeCaps network, use the dynamical routing. Yeah. So first we vectorization the S tree. Second, we use the capsule variable capsule the binary tree the kernel, this kernel to do convolution. And second, we use the static routing. I just mentioned the top A node, and then we will get a fixed size the S tree or fixed side the picture, and then we'll go to the tree capsule network, do the dynamic routing, and get the final result. And this is the whole structure. The experiment is there are 3 data sets for both Python, Java, and C, and the result shows a good result. And he also do ablation study, and he finds that first, if you use the dynamical pooling, that means you use the max pooling, it will not, because it's not suitable for capsule network, it will destroy the spatial and dependency relations between the capsules. So the results seem quite bad here. And for this is for the dimension of the latent representation. If the latent representation is very high, it will introduce sparsity and it will reduce the classification accuracy. But on the contrary, if the dimension of the latent representation is too low, it may not be sufficiently to capture the the variations in the source code. So it will reduce the classification accuracy also. So the 8 is the best. And he also add another capsule layers. So he just stacks the capsule networks, and it also shows a better result.
Okay, let's keep going.
Okay, so that's finished. No
slides. Okay. Okay, thanks, Yufan. So the capsule is still something interesting. It shows it capture another kind of relations once we miss, but such a joint and scientist will show that it's very important. And let's have more detailed discussion on that. Anyone have the questions for the capsule network and how is its application on the program classification? If there are no questions, I suggest that we have let's wait for 5 minutes break, have a 5 minutes break, and we can start with 4:25. Then Siang Hwee will going to give us another paper presentations on program analysis and software engineering. Hello, Siang Hwee. Hello.
Hello.
Yeah,
Hello.
Siang Hwee, maybe you can start.
Okay, sure. Okay, good afternoon, everyone. So today I'll be presenting on feedback-driven semi-supervised synthesis of program transformation. Yeah, the name is a mouthful, but we will be unpacking it bit by bit. Yeah. So the authors for this paper are as follows. They are mainly Microsoft team researchers. So these two PhD students, they did this paper while they were on their internship with Microsoft. Yeah. And their focus is on like program synthesis or program analysis. Yeah. So there are 8 authors for this paper. So that was the first 3, and this is the next 3. So we can see that they are all from the Microsoft Pros team. Yeah. And the last 2 authors. Okay. So to start off, I'll give a little bit of background. So I'm sure a lot of us actually already use IDEs to help us with our code. Yeah. So actually, right now IDE is actually very helpful. It's able to help us edit our code by automating certain edits. So if you have used IDE before, you would know that the IDE can help you auto-generate like certain methods that are always there. For example, like it can help you generate your constructors if you are using Java, or it can help you create your class or like the public static void main, that kind of code blocks. So those are some of the features of an IDE. But more importantly now is that, let's say I have a code that I want to refactor. So actually the IDE is also able to do that. It's able to help you like rename your classes or change certain methods that are used. Yeah. So increasingly there's a trend towards using program synthesis, like creating your own programs and stuff like that. So in this paper itself, actually it's not really about program synthesis per se. It's more about program transformation. So what exactly is program transformation? Maybe it's better if I show you all a video on what exactly program transformation is. Yeah. So over here is a video from the Microsoft team. So yeah. We can see over here. Okay, maybe I'll just run through this. Yeah, we can see over here that he's actually changing a method, like the method signature. And when he's changing this method here called start position, he actually changes certain the signature and the declaration of it. And now when he changes the end position method, he's actually the IDE itself is actually able to give a suggestion as to what should the edit be. So by clicking on it, it actually does the editing for you. So this is pretty small issue, or it's a pretty small change. So if we look at like a code block itself, so over here there's actually, he wants to change this start position method, and we can see that by editing it slightly, so the IDE would actually, yeah, so he did quite a bit of edit. So this edits a lot more than the previous example. And from this case, the IDE actually would give you like certain suggestions of how this edit should be like based on your past history of edits. And not just within this code block itself, but if you see over here, it's able to actually generalize to the rest of your code where similar code blocks actually occur. So yeah, this is what they mean by program transformation. So for certain codes where you actually change it, it's able to help you transform it, making it a lot easier when you do code refactoring. Yeah. Okay, so so that's mainly program transformation. Any questions? Yeah, okay.
It's
I
more
think,
like an editor recommendation, right?
yes, it's like a it's like a edit recommendation, correct? Yeah. So some of the challenges that you will face with this kind of thing is that when you have when you want to transform a program, you want to make sure that your generalization or the transformation is intended, which means that from the model perspective, it needs to create a generalization of this transformation such that it satisfies the given example. So over here, we can see that when the coder first edits its code, that's the example that is giving to the model. And so that is the input. The original string would be the input, and the output is the final string of the edit. Yeah, and then so that's the example, and the generalization model that is created should be able to satisfy this example. And in addition to that, you actually want to be able to produce accurate edits on other parts of the code which the users might not have. Yeah, so there might be other parts of the code that is similar, and this generalization or this transformation should be able to apply to these other parts of the code for it to be efficient for the coder.
By the way, this paper is published in Uppsala, right?
Sorry?
This paper is published in Uppsala. It is a top tier conference
Yeah,
in programming language. Of course, we once did we have a similar work published in FSC, but that's 5 to 6 years ago. You can keep going.
Okay. Yeah. So with regards to this challenge itself, there's actually, we can dissect it further, and there's actually 2 issues here that we want to solve. So like all machine learning kind of problems, we have our true negative, true positive, false negative, and false positive. So in this case, the false negative is when the code block actually, when the unseen input is not similar to the original input that we give, we do not actually want to produce an edit suggestion. Because if we are giving out edit suggestions at every part where it might not even match up, then this actually increases the burden on the developers itself, because they actually need to filter through even more code to find the relevant edits. So in that sense, false negative is we want to be able to locate the similar codes so that we want it to be accurate in locating the similar code blocks. Yeah. Then for false positive is that.
By the way, Yufan, is it Yufan here? Hello, Yufan. Okay, so I think
Hello.
good. Yeah, Yufan. So my suggestion here. So do you remember we want to also your plan, your thesis plan? One of the thesis plans is about the code synthesis. So it's more like we copy and paste 2 part of the code, maybe by code search or by the other means, and we try to have a way to merge those 2 pieces of code. It is basically from another perspective, there's still an edited recommendation. So given 2 pieces of code, how do we recommend additions on those 2 pieces of code so that they can compile well? Hello?
Don't understand.
The point is that giving 2 pieces of code,
Yeah.
one part of your thesis is going to combine and compile these 2 pieces of code.
When do we comply?
Maybe we can have a further discussion on this point. The point is more like maybe we can continue this later. But basically, I suggest you pay more attention on here. So this is about edit. This is a very typical work about editor recommendation or modification recommendation given to a piece of code. When the user will edit 1 part, and this system is going to recommend which part you still need to recommend accordingly, or based on certain rules to recommend the other part of the code which still require recommendation. Basically, it need to recommend where the other editors should happen, and what's the exact editor content should be there, right?
So you mean there are multiple editors?
So my point is that in this work, so you understand the input and output of this approach, right? So the input is that the user applies some editors on some code elements, and the system recommend where the other part requires some other edits, and where are and what are those editors are. So this is what this system, this approach is going to address, right?
Yeah.
And for your approach, do you remember we once have discussed the issue that given 2 pieces of code, how do we merge these 2 pieces of code to satisfy the user's needs?
Yeah.
Right. So basically, our problem can also be transformed into a problem of editor recommendation. So given 2 pieces of code, given 2 pieces of code, how do we edit these 2 pieces of code and then compile and integrate these two pieces of code to satisfy users' need.
Yeah, got it.
Okay. Okay. Siang Hwee, please go on.
Yeah. Okay. Sure. So false negative is to locate the place to edit itself, so that you do for areas that needs edit, you want to locate it, and for areas that don't need editing, you don't want to locate it. Then false positive, on the other hand, is actually after you do a transformation, the transformation should be correct. That means in most simple terms, the transformation after you apply on an unseen input should be the same intended outcome as it was before it was transformed. Yeah. So that those are the two things that need to be considered. Yes. So yeah, okay. So over here I have my first question. So so we know that a transformation, it can be too specific or it can be too general. So yeah, which transformation? So when we say a transformation is too specific, it means that it okay. Yeah. So maybe one of y'all can answer, like, which one do you think would result in false negative and which one would result in false positive? Yeah, so is it that when a transformation is too specific or too general, it will result in false negative? Yeah. Is my question clear?
Here, I would like to be more specific about
Sure.
the transformation, the definition of transformation.
Okay.
So basically, if I understand it correctly, your transformation includes two parts. The first part is location, the coded location. So that means where the transformation should be applied. And then the second step is that what transformation should we apply, right?
Yes, that's correct. That's
so
correct.
the first part is about the location. And the second part, location. And second part is the real transformation, right?
Yes, correct.
So which step I'm talking about is location or
okay, so we would
application?
regard transformation as these two parts itself. So the model would have to apply both. So first you need to do the first step, which is location, and then the second step, which is the transformation.
So your question is just more about the second step, transformation application. You assume that or you means all.
Okay, yeah, actually, okay, maybe my question is not very clear. Because with regards to false negative, it's issue of the location itself. So if my location criteria is too general for okay, we will regard the transformation as these two steps, which is what you said, locating it and then transformation. Correct?
Okay.
Dr. Lee. Yeah, so
okay.
So it's a two-step process. So if the location is wrong already, we wouldn't even transform it. So we can think of this location as a Boolean. It's a Boolean output, whether it's a valid or invalid location. So for it to be false negative, actually is when your location portion of it is too general.
And also the false positive, it have two levels, right? Whether the location is correct.
False positive, your location is correct, but then the transformation here is too specific to my current input. That's why it results in incorrect edit. So actually, yes, you are right that because I'm actually, we discuss it as a whole, like both steps as a whole. So for false negative, it's with regards to the location. And for false positive, we already assume the location is correct. And therefore, if the transformation itself is too specific, which result in an incorrect edit. Yeah. Okay, so yeah, this question is more just to clarify this part here. So yeah, in general, okay, maybe yeah, this part I got the mix up. Yeah. So the false negative is when it's too when your function is okay, yeah. So when
I think it's not
correct,
I think it's not problem.
It's
so sometimes, right, when your rule is too specific.
Correct.
And then you cannot find some.
Yes, you cannot generalize to other areas. Yes, correct. So this part here is too specific. And the second part here is when it's too general, then it will when it's too general, it would result in an incorrect edit. Yeah.
Sometimes I think too specific can also result in the incorrect, right?
Correct. So
Sorry, so just confirm. So
sure,
this
go ahead.
generalization is a combination of the rules that indicate where to apply transformation and what kind of transformation to apply, right? So it's like both.
Yes.
Okay.
Yeah, okay. Actually, with regards to this two-step process, I'll be emphasizing more of it. Yeah, so we actually jumped ahead. Yeah. Okay, so right now out in the market, there is actually quite a few approaches to it. So first is scikit and lace. So these two are actually only able to generalize names of variables, methods, and like the fields itself. Yeah. Scikit is more general. It just uses one example and it synthesizes using the most general example, while lace itself, it uses multiple examples. Yeah, so actually this part on existing approaches is just to showcase what is lacking currently. Yeah, so in general is that if it's too general, for the first one is that it's too general, while the second one is that it's too specific. Yeah, then the closest competitor is actually Rephaser. So Rephaser is able to do it quite consistently. The only issue with Rephaser is that you need quite a lot of repetitive edits before it would start producing some edit suggestions. So based on their test, it can sometimes take up to 6 repetitive edits, which by that point in time, you would actually already have changed most of the source code. Yeah, so what this approach or what this paper wants to do is they actually want to reduce the amount of repetitive edits that needs to be done before it starts producing an edit suggestion. Yeah, so all 3 methods actually only relies on the input and output examples. But this paper, what it wants to do is it actually wants to make use of other abstract syntax trees, so other inputs, other unlabeled inputs in the rest of the projects. So just to be clear is that for this project itself, the input is regarded as a AST, an abstract syntax tree, and the output itself is also a AST. Yeah. Is that clear? Because so essentially, whatever code it was before it was edited, that in itself has its own AST, and that will be the input. And then how the code looks like after it has been edited, that would be the output. Yeah. So this part on using unlabeled AST, it requires a bit of semi-supervision. So it requires a feedback system, either from the user side or an automated method. Yeah. So they actually came up with this idea because they realized that by having more ASTs, even if they are unlabeled, it actually helps to disambiguate the generalization. Yeah, because it actually provides more examples without you even needing to edit it.
Sorry,
Yeah,
sorry, this was answered before. What's an unlabeled AST here in this context?
Okay, so if we recall, right, so unlabeled in this case is that it doesn't have its intended output. So every line of code in your source code can be regarded as a AST, correct? So in this case, the unlabeled AST is okay, the input of this program itself is the AST, is the code that I'm changing. So whatever part of the code that I'm changing before would have its own AST. And after I change it, that's the label of it, that's the output of it. Maybe it's better if I give an example. So over here we see input-output example. So the input in this case is if score is less than limit. And the output here, from a developer's perspective, he changed it to if the score is valid. So if it's valid score. Yeah, so the input AST would look something like that. Correct? And so from if you are asking about an unlabeled AST, right, is that I provide you with this part of the code. Hold on, let me annotate it. Yeah, I provide you with this. This is the AST, but it does not have output. So that's why it's considered unlabeled. And every line of code in your source code can be a unlabeled AST.
So it's actually something that hasn't been processed by the
correct, something that is not not processed by the
hasn't been added by the user. So my follow-up question is that if we want to generate such a transformation or apply through command addition, there must be some trigger, right? So in these papers, I think the trigger is that when some addition happens somewhere else, and I want to recommend whether here need apply some modification here, right? So the input, I'm not sure whether I mentioned correctly. So basically, we're talking about the input and the output of this approach.
Correct.
If I understand correctly, the input first is about the sun addition. So that means sun editors has been applied. So this is more like an action. Then this is ST of the other part. Then we want to generate an ST prime, or more specifically, we want to generate an editor, which equals AST minus ST prime. So this is maybe something we want to recommend. But we want to formalize the, so here I want to formalize want to specify the problem definition.
Okay. Sorry if I wasn't very clear. So actually, in this case, right, the input. So if you recall the video at the start, when he edited the code and stuff like that, the input itself would be the original code. So it would be the original AST.
What I mean is that there's nothing happens. Just give it a piece of code.
So the edit, when an edit occurs, that is the trigger.
So my point is that, so let me clarify my questions. So in this approach, given a piece of code, if nothing happens, will we make any recommendation?
No.
No, right? So the applied editors must be one of the inputs of the methodology. So given a piece of code, or given a code project, when some addition happens on the project, then it will trigger the system to recommend some other recommendation.
Okay. Yeah.
Right. So this is a problem definition.
Yes. Dr. Lin, you are correct in that the input of the system itself is that you need a trigger of the edit. But if you are talking about the input to the model itself, it doesn't actually take in the edit. It just takes in the AST.
Then how they going to leverage the trigger?
So by comparing two AST, you will be able to find out where exactly the edit is.
Okay, so basically, I think this is another form edit. So we have version 1 and version 2, and after the addition, version 1 will be turned into version 2. So basically, they take the additions and the version 2, right, as the input, and recommend other modifications on the project. Let me make it more. So given the code here, this is piece of code, right?
Correct.
So suppose the addition happens here, right? And so the input is, so whatever the model it is, but anyway, so this part is the edits happens, right?
Yeah. Correct.
So it will take the input and edits and the code, and then we're going to the output. It's going to find a place. Maybe we recommend a location plus the transformed content or a new edits, right? So maybe this is a pair. We may recommend a sequence of location and the edits on the location. So this is a problem definition. Or yes or no, or you understand, or our understanding is a little bit different.
Okay, so based on my understanding of the paper itself, so maybe my understanding of the paper is a bit off, but the idea is that when we are training when we are training this transformation program, you will be giving it the input and the output. Yes, correct.
Yeah.
And
so what
when
you about
trigger this transformation program, it's based when you do the edit. Yes.
Will you please repeat the last sentence?
Okay, so because after you edit the file, so after you convert from this line over here to this line over here.
Mm.
So okay, we think of it in the video demo that I showed just now. So he's actually editing the code. So at the initial phase, before he edited the code, this was how the code looks like. And after he edited the code, this is how the code looks like. So these two, the AST of this and the AST of this will be used to so-called guide the transformation for the rest of the code.
Yeah, so I think okay, so in this case, I think my understanding is correct. So the input is just an editor. The input is editor. So this part you can call this is a transformation. It's more academic terminologies, but if for our discussion we just use the term
It's just an edit.
it's just editor. So basically it's just when editor happening on our code, we want to recommend where else need some new edits, right? So this is the basic the problem definition. So when we're talking about the problem, we need to be very, very clear about the concepts and the problem definition so that based on which we can further our discussion.
Okay.
Okay.
Yeah.
Okay, let's keep going.
Sure. Yeah. So over here I actually have another question about how the AST will look like. But in the interest of time, I would just show the AST for this. So the AST for the its valid score will look something like that. So I think we are pretty clear about how this AST will look. Yeah. Okay. So we can see that these two portions of it are where the changes of the code actually occur, and the program itself, this transformation program, will track which part of the subtrees were actually used to construct the output. So we'll notice that this score variable is actually consistent across both the input and the output. So it's maintained. Yeah. Okay. So so this is just a very basic step of comparing the two input and output. Yeah. So after that, this is where the program actually brings in their novelty and look for additional inputs that might help to actually refine this generalization. So over here, it actually performs two steps. First part is anti-unification, and the second part is a feedback system. So for anti-unification, right? So I'll give another example on how it works. Yeah. So over here on the left side, we have the transformation or the edit from the previous slide, which is the if score less than limit, then it's edited to if it's valid score. Yeah. So now over here, I have two other code blocks that might be related. So for the first one is it will look something like that. So over here we can see that this is unlabeled because it has no output. It only has the code itself. Yeah. So Darren, in terms of unlabeled AST, this is what it meant. Yeah, or unlabeled input, this is what I meant. It's just a code block on its own that doesn't have a corresponding output. Yeah. So okay. This code block will look, the AST of this code block will look something like this, which if we compare it, it's actually very similar to the original code block. Yeah. Or the original AST over here. Then on the other hand, if let's say we have some unrelated condition, so the AST of the unrelated condition will look something like this. Yeah, correct. So over here the decision by the algorithm is that it will actually keep this block. In fact, it would edit it so that it will look something like this, but it will just replace the score with a get score run. Is this clear over here? Yeah, so it's just a simple mapping from, so because they know that this part here it's similar. So this is the first step, which is the localization step.
So maybe I raise a question for the audience.
Sure.
So maybe Darren or other students can have a try. So what is the purpose to find those anti-unification, or what is the purpose to find similar AST trees, like if you get a score wrong in a smaller than limit? Anyone would like to have a guess and have a try? Darren or Yufan, would you want to have a try?
Well, I guess the idea is that is to do with like those typical like software engineering ideas, right? So like the developer in the first case, if the developer changes score as the limit to a condition is valid score, then you want to apply this transformation to other cases where it's the similar case so that you can presumably you improve the code by applying the same transformation to a similar case. So it's what I'm trying to do by looking like you can identify similar patterns in the AST, then you apply transformation with similar patterns versus those unrelated conditions.
Exactly. So basically, the similarity is evidence or the basis for whether we need to apply or propagate such editors on this location, right, Siang Hwee?
Yes, correct.
Mm.
Okay. So yeah. So pretty much, this is the anti-unification process. I would dive deeper into their actual implementation later. Yeah. Then after you because after you anti-unify it, there is still a feedback system because you are not certain whether the input whether this input should be accepted as a valid transformation or not. So this is where there is a feedback system. So this feedback system can come in two forms. The feedback system uses a reward function, or for a less technical term, it just scores this edit to see whether this edit should be accepted or rejected. So this reward function can occur in two ways. So the first way is that the user themselves, of course, assuming we are editing the code on an IDE, so the user themselves can actually provide the feedback whether yes, I want to accept this change or no. Then that is very clear cut.
How do they? So I understand that acceptance and rejections will be a very useful feedback.
Yeah.
So my question is that how do they design the UI? So do they mark some things or such a feedback is collected during the programming, and the user do not need to deliver to like specify their decision of acceptance and rejection?
Okay, so based on the UI side is if we recall the video, so what happened was that after he has done 2 edits, so the second example of the video, after he has done 2 edits, there's actually like a light bulb there where if you click on it, it actually points you to other locations which might need edit. So over there, it can just be a list of the locations which has been narrowed down that is similar and can be edited in this form. So that is the UI perspective of it. Do I make myself clear?
So let me rephrase. So once they give editors, when they give the recommendations, so if I understand it correctly, and sometimes user will adapt such exceptions, or if they do not adapt such exception, we consider it as a rejection.
Yes.
Or, yeah, so it's more like a way to lighten the design.
Sorry, can you
the lightweighted design, that means we collect the feedback, but do not require a lot of users' effort to specify the feedback.
yes.
Yes. So the point is here. So the feedback is a very important concept in the subject of software engineering. So here I would like to clarify the research of the software engineering and the course of software engineering. So when some people saying the software engineering is simple, and the reason is that from the perspective of software engineering course, we learn the waterfall model and what is requirement, what is design, and what is test, right? So that's the basic idea. But the software engineering research is basically to automate the program activity. So actually they're in different levels. They're in different, totally different aspects. So in the software engineering fields, and the way important is to take the human into the loop. So that is how the feedback system will be, how the feedback system can work here. But how to design the feedback is very important. So in terms of how to design the feedback, there's another subject or another type of research work called HCI. It's called the human-computer interaction. So this part of work we're deliberately design how to design intuitive user interface for people to better interact with the system. And then it will involve a lot of the UI design expertise, psychology, and computer science. Okay, I just mentioned this a little bit. Then you can keep going on.
Yeah. Okay. Yeah. So mainly the reward functions, it can be user provided, which will require the interactions that we mentioned, or it can be automated in terms of after the edit itself, whether the code compiles or things like that. Yes. So those are some ways to come up with a reward function. Yeah. The actual reward function is up to the users itself. Yeah. So now, so with these few examples, I hope that you all have a bigger picture of how and what we are trying to solve over here. Yeah. So now to the more technical terms and the more technical part of the paper. So we are actually going to formalize the problem properly. So these are some of the symbols that will be used. It's not very symbol heavy, so don't worry about that. Yeah. So the first symbol is T itself. T is the set of all ASTs. Other than that, is the subtrees itself. So subtrees is a set of all the subtrees in T itself. And for this paper itself, they believe that their AST, or they design their AST such that each node of the AST consists of a few things. It consists of three things. First thing is the label itself, representing the node type. So the node itself can be an identifier, it can be a method declaration, it can be like a comparator or something like that. Then the next one is the set of attributes, which is the actual value of the node itself. So in our case, like the comparator, or for example, identifier, just now the score, the limits, those would have a value associated with it. And then the last part of it is actually the children AST. So if it's the child node, it's possible that it doesn't have any children AST as well. Yeah, so this is essentially how they design their AST to be like. Then the second part is P, which is a partial functions that maps AST to another AST. So this is actually the transformation function that we were discussing all along. So as Dr. Lin has mentioned just now, is that it's actually split into two parts. So there's a guard part. The guard part is actually a Boolean. It returns a Boolean variable. It returns a Boolean value as to whether or not a transformation should be done onto this AST. And then the actual transformation, which is the P trans itself. So simply put, is when you apply P onto a AST, it will transform if it matches the guard conditions. If not, it will not transform and it will not return any output. Yeah, so I think this is pretty clear cut on. So it's like Dr. Lin mentioned just now, it's a two-step process. First, it checks if the ASTs matches that of the guard itself, and then if it does, then it will transform. If not, it wouldn't. Yeah. Any questions with regards to this? Okay, yeah, if not, I'll move on. So another example, just to be a bit more clear about how the guard and the transformation would look like. So over here, we actually have two examples. The first one is it changes the method signature again. So from the repository over here, so maybe just to speed it up a bit, I'll just highlight the important changes. So over here, the repository is actually moved into the method parameters itself. And yeah, that's mainly and it change it to like a static class, static call. Yeah. So from it, this is the same transformation for both sides. So we can see that repository is moved to the parameter and it changed it to a static call. So over here, we can see that the P guard looks at the AST. So the original AST, which looks like this. So after giving it two inputs, so for example, this input and this input, these two are an input. The red ones are the input. So it would do like a Boolean matching to see whether matches certain whether they have similar structure. Yeah. So for example, we can see that this repository repository.resolve dependency would look something like that. So repository will be x1, resolve dependency will be x2, and then x3, x4, x5, and x6 would be the parameters itself. So based on this input, the one on top and the input below, we actually can get a Boolean, it's a logic like that, whereby if it fulfills all these criteria, it returns true. If not, it will return false. So the x1 label must be equal to repository. The x2 label must be equal to resolve dependency. So notice that actually in this case, x3 over here is dependency 1 and x3 over here is dependency 2. So we can see that x3 in both examples or in both inputs are different. So because of that, in our Boolean over here, we will notice that we ignore the text value of x3. Yeah, so the idea is the more examples you get, it helps to make your p-guard a bit more general. Yes.
A minor question here is that
Sure.
How do they design the match? Is there an exact rule to define the match function? So, for example, whether the text value always matters.
Whether the text
value and also sometimes the text value will be changed a little bit. For example, in this case, we just need to copy. We just need to copy all the parameters in some method call, right?
Correct.
So what if the method the number of the parameters is increase or decrease a little bit, and how does the rules to define? How can we define the rule there?
Okay, so when we talk about increase, you mean like from the input to the output?
I mean the match function. So
yes,
when the editor is applied on a function call with 4 parameters, right? So
yes.
Here there's the regular expression like mentioned here. So what if we have one less parameters? Or what if I have one more parameters? Will the match will still be triggered? Will it still trigger the p-guard? The p-guard value will still be true or not?
Okay, in this case, the p-guard value will not be true anymore. Yes, because this is the what I'm describing over here, the p-guard and the p-trans is actually what is currently in the market. It is it doesn't use the semi-supervised learning method yet. This is just in general. So if we recall the example, so this edit would be you will need to take in a few edits before it gives some suggestions. Correct.
And by the way, so the rule of match is learned or predefined?
It's learned.
It's learned. Okay.
Yeah. So for example, maybe with only one example over here. So maybe with the first example, we would see that x3.label might be set to dependency 1. But then after the second edit, then x3.label, the text value need not be dependency 1 anymore. So it slowly generalizes. With more example, it slowly generalizes.
I got it. So it will start with a very specific
very
specific. And with the example, the number of examples increased, it will gradually generalize that. And I hope that there's a rule which can adapt all the small number of the edited examples. And so my follow-up question is that if they adopt this way, it requires a lot of feedbacks, right? So for example, if the first if we have one editor, we have very specific rules, but those rules need to be generalized, can be generalized, but with a large number of editors as learning examples. So into the methodologies separate from these problems. So if it requires so many feedbacks, will the tool was still used for?
Okay, I guess in this case, when you mean so many feedback is for this example, okay, just using these two example, the first so-called user, the part where the user intervenes is when he edits from this code to this code. This is the first edit that the user does. So maybe from the IDE perspective, it does not recognize this to be similar to this because the pguard fails, correct? Yeah. So at this point, yes, the user would need to so-called feedback and edit this manually to let the program knows that this should be edited in this way also. And by looking at the history, so yes, they involve quite a bit of feedback in the sense that he needs to edit.
By the way, when the user provides feedback, will the user tell the system that the second line is supposed to be matched with the first line?
No, it's purely just changing it. By right, the ID itself would maintain a array or list of the history edits.
So basically there's still a similarity measurement for the editors.
Yes, correct. I guess it's the exact similarity measurement, I'm not too sure, but I guess it's with regards to how similar this pguard looks.
Yeah, I got it. So let's keep going on. I think I got the basic idea of this approach. I just wonder maybe the writing will be so good so that this paper can squeeze into.
Oh yeah, okay. This part here is still more of a background of what is the current state. So this is how all the existing approaches do their edit. So like the pguard and the p transformation. So yeah, the transformation itself is just you'll see it just matches to what was edited. Yeah. Okay, so that's it. So now to the actual crux of the paper, or yeah, it's about the semi-supervised part of it. So it allows the users themselves to actually control the level of generalization by it wants to allow the users to control the level of generalization. So for this case itself, instead of just input and output examples, there are a few other things. So there is a positive inputs, which means that they are inputs that should be edited. And then there's negative inputs, which are inputs that shouldn't be edited. So given these three things, input, output examples, which we can regard it as a pair of AST. So input and an output AST. Positive inputs, which is just a single AST, and a negative input, which is also a single AST. You want to produce a P. So P, recall that P is actually a pair of functions which consists of pguard and p transform, such that the P itself is consistent with all the input-output examples. And for every positive input, it produces an output. So it produces an output doesn't mean that the output is right. It just means that it managed to localize and say that the output, that input actually passes through the guard, the pguard itself. And it does not produce an output on all the negative inputs. So these inputs do not pass through the pguards. Yeah. So this is the problem that they are trying to solve, which is by taking in additional inputs and try to make it even more general. Yeah. Okay, so yeah, this is the SSP problem that they are trying to solve. But this problem actually assumes access to additional positive and negative input. So we notice that we need to take in two more parameters, the positive and the negative inputs. So how can we do or generate these positive and negative inputs? It actually use feedback from the users itself. Yeah. So at this part on the feedback is where a reward function comes into play, and it maps the tree itself to a reward, to a value, to see whether it's how should I put it? To see whether it's valid or not. Yeah. So this feedback mechanism, as mentioned previously, it can be user feedback, or it can actually use other forms of factor, like whether the source code is compilable, or whether the edit output is actually similar to the example outputs that is given. Yeah. So this feedback portion is actually done in an iterative manner. It's very similar to like a reinforcement learning kind of problem. So before any other questions, so I'll show the workflow of it first. So the workflow of how this whole process works is that at the start, at the first iteration, there's actually no positive inputs, there's no negative inputs. So all that we have is the example, the input and output examples that the user provides. So this will be passed into this synthesizer, which generates a program P that contains of the P guard and the P transform. Then from this P guard and P transform this P is actually passed on to this part over here where the feedback actually occurs. So over here we see input pool. So input pool in this case, at least in the paper's case, is all the ASTs that are within this source code itself. Yeah. So over here, by using this P, which consists of the P guard and the P transform and all the ASTs in this input pool, it would actually go through this feedback process, and a portion of it can be done by the user. Or if we want to do for fully automated, then we can remove the user and just purely use the environment. From this feedback function itself, so this part here is where the feedback occurs, there will be a reward value associated with each input. So this reward, depending on whether it's more than a certain threshold or less than a certain threshold, it would be added to the positive and the negative input. Yeah. So at the next iteration, this synthesizer, it takes in the examples from the positive inputs as well as the negative inputs and the existing input-output examples. And then it will generate a more general program, which would include the positive inputs but exclude the negative inputs. Any questions up to now?
I think it's very straightforward and
Yes.
very clear.
Right.
Keep going.
Yeah. Okay. So actually in this case, right, unlike maybe a machine learning project where we look at the accuracy or recall, the actual optimization criteria over here, because it's really just to aid the developers in editing their code more conveniently. So the optimization here is how well does this program actually matches the user intent. So yeah, I think that is something that is a bit more special about this program itself. So yeah, so okay, down to the source code itself. So we'll start off with the semi-supervised synthesizer, which is over here. So for this step, okay, this is the main source code for it, but don't worry, we'll be going through it line by line. So the first line itself talks about the inputs. It retrieves all the inputs from the input-output examples that we have. Then over here, it actually makes use. So over here, you see a rephaser guard. So this rephaser is one of the existing algorithms. So this program actually builds on the existing algorithms. So it uses the guard function of this rephaser to help create its own guard function. Yeah. So over here, the guard function will take in the inputs as well as the inputs union with the positive inputs, which at the start is a null set, and the negative input, which is also a null set at the start. Then over here, it goes into transient. So transient over here is at line 7. Yeah, transient over here takes in the examples, which is the input-output examples, as well as the positive inputs. So the reason for this is because if it's a negative input, it would already be, if it's a negative input, it would already be blocked by the guard step. So it would not even reach the p-trans method. So over here, we are actually only concerned with the input-output examples as well as the positive inputs. So over here, it makes use of the transform clause from the existing algorithm on all the input output examples. So this is already something that is done by the existing algorithm because you give it the input and the output. Yeah. And then over here, it uses provenance. So provenance, it's what we saw just now. So if you recall the example on if score is less than limit, so we noticed that score is common between the input and the output. So this is what the provenance portion of it does. So it keeps track of the variable that is common between the input and the output, and it just keeps track of it. Yeah, so this is done for each example that is in the input output example. Any questions up to here? So this provenance here, you can think of it as like it keeps track of the variables that are used in the inputs and the output.
I think that would be quite straightforward.
Yeah.
So basically, there's supposed to be the similarity measurement for deciding whether there's supposed to be provenance, right?
Yes, correct.
Okay, keep going.
Okay, yeah. So so up to here, if it's fine, then now we look at this line over here. So this line over here, this symbol, this bow tie symbol, it actually represents the anti-unification. So so let's get back to the example that we had previously. So over here, this anti-unification, it takes in all the inputs as well as the positive inputs. So if we look at the input here, this is the positive input. So I1 in this case is if score less than limit, which has an AST that looks like that. And I2, which is actually PI0, is actually if get score run is less than limit. So these two are one is the input from the input output examples, and one is the input from the positive inputs. Yeah, so the anti-unification of these two will be it can be described in such a manner, which is that if H0, where H0 is a variable that is constantly changing, is less than limit, then for the first example, H0 will be mapped to score, and for the second example, H0 will be mapped to get score right. Yeah. So essentially, based on these two AST itself, it comes out with the most specific H0. So H in this case, we can consider it a hole. So a hole that can be filled up by any other variable. So these two AST, they are similar in terms of. So this part we are still looking at the guide itself. It's not looking at the transformation yet, but we can see that these two AST are similar in the right-hand side of the tree. So they would keep the right-hand side of the tree, and then they would make the left-hand side of the tree, which is this part here, the H0. So this hole would be filled up depending on the examples itself. Yeah.
Okay.
Okay. So yes, then so if there exists a case whereby it's not able to find proper unification, so that means among all of this mapping, if there exists a case whereby H0 cannot be mapped to another thing, then that means that the p-guide, there's an issue with the p-guide. There's a negative input already. Yeah, so that's when it returns null set. Yeah, or it returns nothing. Yeah, if not, the additional examples. Hold on. Yeah, the additional examples will just be the positive inputs. So out of all these positive input, it will be evaluated using the trans function that we generated in line 8, as well as the positive input. And over here, we also take in a value I. So this I is, this evaluation function, what it does is, apart from the user, so we mentioned just now that this is like apart from evaluating whether it can compile and stuff like that, it also checks how similar PI is to I. So that's why there's input here. So I in this case is an input from the input output examples. Yeah. And then by evaluating it, now you have a mapping of a positive input to its expected output. And this helps you to generate more examples. Yeah. Any questions up to here?
I think that's very natural
Yeah.
and a very good, very clarified explanations.
Okay, yeah, thank you. So moving on. So now we are done with this. By the end of this step, the previous step, we actually went through this semi-supervised synthesis, and we have a program over here which takes in pGut and ptrans. Yep. So now over here we are going to do the feedback portion of things. Yeah. So feedback, as mentioned, there are actually a few ways to do the feedback. So I'll start off with the most simple one, which is the user feedback. So it just takes purely the user feedback. Yeah. So over here, this code block actually represents the entire flow in this graph in this flow chart over here. So over here we can see that P is synthesized engine, which is the code block from the previous two slides. Yeah. Then after P has been generated, which is the pGut and the P transform as well, it would notify the users of the new suggestions that are given. Yes. So that means all the new positive inputs that are given, it will be it would inform the users. And then over here, the users would actually feedback on whether the examples are accurate or not. So in this case, because it's a user input, there's actually no like scoring per se. It's very clear cut. If it's a positive input and the user defines it as a positive input, then it has the maximum score, which is maximum infinity. And then if it's the negative input and the user defines it to be, and the user feedbacks that it is a negative input, then it will be a negative infinity. Yeah. Then based on this, it will generate a new PI prime and a NI prime. Yes, based on the threshold values. So because this is user, this requires user feedback. So actually, this the positive inputs will always be positive inputs, and the negative inputs will always be negative inputs. Yes. So this part might seem a bit counterintuitive, but it's because this reward function, this feedback function, can actually be changed depending on whether it's looking at user feedback or automated feedback function. Yeah. So I think the user feedback function doesn't provide much of there isn't much to talk about for the user feedback portion. So we will go into the automated feedback itself. So this automated feedback, we can see that it's a lot longer. It actually replaces this line 4 over here to give a new reward value. So for this step, we'll run through it again. It might look a bit complicated, but it's actually pretty straightforward as well. So over here, it uses the provenance again from the input and output example. So over here, we take an arbitrary example because by right, all of these examples should have a similar transformation. Yeah, so any arbitrary example would be taken from here. And to prevent repeated calculation, actually this part of the provenance can be taken from the synthesizer itself. Then over here, it initializes a reward function. So this a reward array or a reward list. Yeah, so then now it iterates through all the input in the input pool. So for each of the input in the input pool, it actually does compile. It does a few things. So first thing, it checks if PI is whether PI exists. So actually from this first check, most of it would have been most of the input from the input pool would have been X, because this PI not equal to now is actually the pGut, what the pGut does. So for most of the input in the input pool, it would fail at the first one. So if it manages to pass the first one, it would actually compile it. And if it fails to compile, then we can agree that this is a negative input, because this transformation would not is definitely not a valid transformation, because it causes the program to fail. So because of that, we would set the value of this input to be negative infinity. So it's a negative example. Yeah. So this part should be pretty clear. So just to reiterate, the first part here, the first Boolean condition makes use of the pGut. So if if it doesn't even pass the PGAT, it would not even do the compilation. So the reason for this is that compiling is actually very costly. So some of the benefits of an IDE is that it allows incremental compilation. So even though there might be quite a lot of compiling over here, because there's incremental compilation, it reduces the cost. And because most of the input actually fills the first Boolean condition, it actually reduces the cost significantly. Yeah. Then for the next step, which is this part over here, based on this new input. So as of this point here, we know that this input is a valid input. It's able to compile. And from this valid input, we want to create a new guard function. So this guard function, if the guard function is below a certain threshold, we actually reject it. Yeah, so what they are trying to do over here is that they actually create a new guard and then they check if the guard is too general or if the guard is too general. Because if our guard is too general, it will actually allow a lot of these inputs to come in. So because of that, if the guard is too general, it means that this positive input, even though it's a positive input, it's not a very good, it's not a input that we should be including. Because it will read.
I think here it introduced a lot of rules here in this algorithm. I think you make a perfect clarification here. So, but from our researchers, we can stand at a higher standard to think about their work, right? So, if I'm going to make a comment here, so the first is that uncompilable code may not necessarily be a useless code. So this is my first comment. Sometimes the transformation, when we apply the transformation, even if the code is not compilable, it sometimes still brings us some valuable information on how to modify the code. So maybe if we involve the human feedback, maybe a minor change can just make uncompilable code into a compilable code. And the second is that I understand it makes sense. Suppose the guard is too small than a threshold. So for the whole methodologies, it does not apply in a machine learning approach, right?
Correct.
So
It's not machine learning.
It set a lot of rules and it's a threshold. It merge and compile. And here and how to merge it is to use the rephaser technique to merge the more generalized example. Have I made myself understood? So
yeah,
the point
correct.
is that, so suppose we have get a score and a score, right? And how do we abstract such a slot in the template? So they just using some existing merge algorithm. They do not use the other algorithm there.
Correct. They never actually their new algorithm just actually relies a lot on the existing.
Okay,
algorithm.
so maybe we can skip this reward part, and I think we can learn little about this, and I think we can go forward to see the next slides. Yeah.
Okay. Yeah. Sure. So this part here is after that it just does actually it's just one more line over here. It just does a comparison between the current input and the arbitrary input from the start to see how similar they are. And if they are similar, then it's good if they are similar. So this here is how they score it based on a similarity index over here. Yeah. Okay, so actually after this is the main contribution to their feedback-driven part of it. Yes.
Okay. I understand they involve a non-trivial engineering effort, especially their work supposed to be integrated into Microsoft Visual Studio, right?
Yes, it's integrated to Visual Studio. I'm not too sure whether it's integrated yet, but
there's a prototype. There must be a prototype. Yeah. So, but anyways, this is definitely a very solid work integrated to IDE. And in terms of the novelty, I don't know. But definitely it's a very good software engineering work. But I'm not sure how UPSLA reviewers can look into this kind of work. Let's keep going on. Yeah.
Okay, the rest of the slides are mainly on the experiment itself to show how well their new model performed. So they actually we keep saying rephaser, and they actually compare their new model with the old rephaser.
And by the way, how do they do experiment regarding user feedback?
Using yes, okay, that would be the user feedback portion of it, is it?
Right. So how do they? So they usually have two ways to do this. The first is that they conduct user study. So they will have the real people to provide the feedback. On the other hand, they can simulate the user feedback by a robot. Both will be fine. Yeah.
Correct. Because in this case, I think their user feedback is should be their own programmer. So here actually the main comparison is that one has feedback and one doesn't have feedback. So the rephaser doesn't use user feedback at all. Yeah. So
yeah, I understand. I understand. I understand there's a user, but how they get the user feedback in the experiment?
I think they didn't specify that.
They supposed to be specified, right? So we went doing something. We went have a work very similar to their approach. And there, since the user feedback is a major difference, or the main novelty introduced in this work. So how to generate user feedback matters quite a lot in the evaluation.
How to generate?
Yeah. So here, so if I'm the one who present this work, I think I will quickly go through the feedback part because there's all the existing work. Maybe from your stage, you focus a lot on the technical design and what is the technical contribution, and whether there's a better technique I can learn about it. But from the research point of view, I will focus more on the evaluation part. So usually when we are doing research, people focus a lot on the technical design because they believe that technical design matters quite a lot. The fancier the technique, the more formula it is, the more algorithm, the more pseudo algorithm there in the paper. It seems a seemingly solid work based on those presentation. But usually when we evaluate the work, we look into, and the evaluation experiment take a very, very important part of it. Okay, let's keep going on.
Yeah. Okay. Actually, for the most part of this, it's just that their precision and recall is way better. So based on one example only, because one example if you think about it from their gut perspective, the rephaser gut is not able to actually generalize to other examples. So because of that, the recall is actually very low. But after with more examples, it actually performs better.
By the way, so a small question. Recall means that we should apply the edits, but it's missed, right?
Yes, correct.
And how does the user now provide a feedback for the missing edits?
For which part here?
And the recall is that we're supposed to be apply some transformation or editor on some code, right? But a small recall means that we miss a lot of such edits.
Correct.
And my question is that for how does the feedback addressing the missing editor problem?
Oh, from their new rephaser perspective.
Yes.
Okay. Because of their loop itself, they actually managed to take in more positive inputs. So actually, even though I only give one input-output examples, it's actually able to take in more positive inputs.
So the positive inputs lies in the user trying to, for example, if there's no recall or there is a false negative, means that there's no recommendation. So how does the user address the problem when there should be a recommendation, but there's no recommendations in practice? Yeah.
Oh, in practice. Okay. So so in practice, what would happen is, let's say there's no recommendation, so you would have to find the next part which should be edited, and then you edit
manually.
Yes, manually for the
Okay,
replacer
so
part.
basically they're trying to yeah, I got it. So basically there's more manually find where it should be edited, where you edited this part, and the system recorded it and applied the generalization. That sounds fairly straightforward.
Correct. That's the replacer method.
Okay, let's keep going on. Maybe
Yeah.
I think that's one advantage. So the university work with a big company like Microsoft. So because of the endorsement of Microsoft, the reviewers will be more convinced that this work is very, very useful. And despite, I think from the technical contribution part, I find this just okay, but definitely they involve the non-trivial engineering work and how to adapt, how to coding the feedback, etc. Okay, let's keep going on. Yeah.
Yeah, okay. Then after that, they also check their effectiveness of the reward function. So from the reward function, the automated reward function that we have just now. So when there is no validation, which means there's actually no reward function, so everything is just positive infinity, which means that everything will just be accepted. Then the next layer is clone detection, which means that they actually compare candidate input with a valid input using clone detection technique. So how similar the candidate input is to the input itself. Yeah, this is the so-called basic form of a reward calculation based on similarity between the input and the candidate input. And the last one is the reward function, which was in the slide, the previous slide 3 slides ago. Yeah, and based on that, without validation, so there will obviously be a lot of false positive because everything goes through. So that is obviously, I feel this might not be a fair comparison.
I think that's it. So because you involve a lot of human feedback, the human feedback deliberately told us that which code was supposed to be can be unified and be generalized. So I think there's nothing special. But my question is that whether they conduct a large scale user study or they're going to use simulated experiment for that. So that is really matters to me. And yeah, so you can think about it when we are reading the paper, we're not. So when you read the paper, you spend a lot of effort time to read the paper, right? And the reward, the benefit is that this paper can contribute a lot to a FYP project or the future functional university application. And hopefully this publication can be beneficial to us in the future. So basically we need to grasp and extract the most informative and meaningful information from the paper. I think that is that is what we want. I think from this paper, I think you can use very little about their technical design, but this is just based on what my judgment may or may not right.
Yes.
But if we want to be for example, if we want to go to the United States and further study as a PhD student, so how to design a study based on such a technology, it matters a lot. Right. So how to make your experiment convincing and make the reviewer believe that the work is really feasible and practical. So that is so you can, when we read the papers, a lot of the technique, for example, how they design the word functions, that really matters. If we don't read the paper, we can design the word function by ourselves. There's nothing special there. And in terms of feedback, I think the feedback is also not a very, very novel idea, because a lot of papers in the recent 10 years propose a lot of the feedback candidates. But what matters is that how do they propose such a feedback? And finally get their paper accepted in the top tier programming language conference. So that is what matters to, of course, it matters a lot to me. And I think for FYPs and how you design, for example, Darren's and Siang Hwee, you will have FYP, and finally you will have experiment design. And how to design the experiment, make it more convincing. Well, that matters to us.
Okay, yeah, okay. So I guess maybe my focus for this paper
Yeah,
was
I
a
think
bit wrong.
that's quite understandable. That's really quite understandable. I just make a comment here.
Yeah.
And just to make sure that in the future when you read the paper, you spend your valuable effort and times on something most important.
Okay, can. I think with regards to that, I will need to take.
Maybe you can have you can revisit the paper in
Yes.
terms of how they generate the feedback. And then maybe you can have update in our individual meetings.
Okay, sure.
Okay, let's keep moving on. Maybe I think it's almost until the end.
Actually, this part here is also just another experiment which shows that even though they compare blue pencil. So blue pencil is actually what we saw, the first video demo that we saw. So that was blue pencil, and then they actually have two variants of blue pencil. The first one is so-called the user feedback. So how the user gives feedback in this case is by the cursor location. So when the user actually puts the cursor at the part of the code that you want to change, then that's where it kind of gives the model an idea that this is the AST that the user is interested in. And then the transformation model would then provide the user with the appropriate edit. So this is one way that it can be done in a user-driven manner, which is by giving it like some form of sensing which part of the AST exactly they are interested in. Yes.
Okay,
Correct.
so this is more like a case study or operation study.
Correct.
Okay.
Yeah, and even though there's a bit more of a time increase, it's insignificant. Yeah. Okay. Yeah. And pretty much that's it for this presentation. Yeah.
Okay. Thanks, Siang Hwee. I think you make a very perfect and excellent presentations. Despite a lot of students is gone, but I really appreciate your presentations. But in terms of researchers, you can have more focus not only on the technical design, but also on the experiment. So the point is that when we are designing experiment, and how do we make sure in these paper presentations, this experiment makes the technical design looks more convincing. So that's the part. This is a comment we're gonna make. Okay.
Okay. Yeah, I'll take note of that next time.
Yeah. Thanks, Siang Hwee. Yeah, very excellent.
Thank you.
Okay, let's go today. Thanks everyone for keeping until this end. Okay, let's go today then. Bye.
Thanks all. Bye.
Thanks. Bye.